Hi, folks. Today we're going to talk about mathematics. We're going to go back to the start. And so, what is mathematics? At the beginning of this series, we asked the question, what is mathematics? Having now surveyed a variety of topics in math, we now have the tools needed to effectively answer this question. The goal for today's lesson is to revisit the topics we've explored and see if we can gain a deeper understanding of what mathematics is all about. And so before we even introduced the idea of numbers, we started with patterns, the idea of patterns. There are linear patterns, patterns for numbers, but also things like music. Ultimately, an understanding of patterns is what mathematics is all about, as we seek to take inductive reasoning and connect it to deductive reasoning. Math history. We then did a deep dive into math history. What became clear was that the history of math was just a reflection of the history of humanity. While there were eras of great advancement in mathematics, there were equally moments of loss. As people migrate, they take math with them, and the math has grown over the millennia into what we have today. Number sets. So after exploring history, we transitioned to more concrete math topics by exploring sets and numbers. Our first exploration involved developing sets of numbers which we could explore. These number sets were things we'd mostly seen before, but now we could explore how they are connected to one another, building to an idea of general sets. Number theory felt a natural introduction into thinking more abstractly. We are familiar with the structures of number theory, but we may not have explored it as thoroughly. Our algorithms from arithmetic are all based on observations and provable relations, all of which is built on the structures of our standard counting numbers. But now we could actually go back and think through all of it. What was it that was connecting this structure of numbers? Techniques of proof. With our understanding of numbers as a foundation, we built the idea of proofs. In mathematics, we seek to determine what is true and false. Theorems are our proven objects, and the proof is how we reach them. Mathematics at its core is the study of certainty, built on conditional statements and rigorous definitions. And these techniques are how we divine this certainty. Set theory. With numbers as our primary example, we then built the idea of sets in a more general sense. A set is just a collection of objects. That's all it is. And so set theory served as the foundation of most of the other branches of math we explored in this course. And so understanding what it means to be an element, a subset, and a set was an essential foundation. Venn diagrams. As a part of set theory, we explored the idea of Venn and Euler diagrams. When we have two sets, what do the sets have in common? What do they not have in common? This idea of what things have in common would become a theme as we explored more complicated sets and structures. Equivalence relations. An additional tool we needed was the idea of equivalence. Beginning with only the structure of sets, we don't have the tools of arithmetic, and we had to build them from scratch. In the case of equivalence relations, we developed an understanding of what it meant for things to be equal, and what we can do with things which are equal. Point set topology. Topology was a natural extension of set theory topics. And so a topology is a structure which is created from the unions and intersections of sets. When we think of the structures of things, the existence of a topology is one of the easiest ways to describe a structure in a way where we can do math on it. Manifolds. With the structures of topology, we were able to explore objects from differential topology and differential geometry called manifolds. A manifold is just an object which locally looks like a plane, 3 space, or Rn for some n. We suspect that the universe itself is a manifold with 3 spatial dimensions, I can't spell spatial, and 1 time dimension. And we know that the rules are slightly different from the Cartesian coordinate system. Topological equivalence. And so topological objects often share a similar structure, even if their geometry may be a little different. To define this topological equivalence, we explored the ideas of homeomorphisms and homotopy. In understanding these ideas of equivalence, we were able to explore how similar all things are. Graph theory. While topology is all about exploring the structure of things through commonalities, graph theory gave us a way to explore how things are connected. We explored the classical examples, but really an understanding of how things are connected is applicable to all fields. Applied math. With graph theory, we finally could discuss the fundamentals of applied mathematics. In applying mathematics to other fields, we have a use for all these abstract structures we've been talking about. Graph theory in particular is present in nearly every field, and so a strong understanding of graphs gives us a deeper understanding of all fields. Algebraic structures. Up to this point, we had only focused on the structures of things. In introducing algebraic structures and properties, we created binary operations, which allow us to do things within our structures. These properties are the underlying structures of algebra and arithmetic. Even numbers themselves are described in relation to one another using these structures. Group theory. With the algebraic properties came different collections of algebraic properties, in particular groups, rings, and fields. A group is just a set and operation which satisfy 4 core properties, but there are so many different operations which satisfy these same 4 properties. It gave us a way to compare the motions of a clock to the structure of the atom. Euclidean geometry. Transitioning into our unit on geometry and the study of change, we began with Euclidean geometry. Euclidean geometry is the geometry of Euclid's The Element, which has served as one of the foundations of mathematics for over 2,000 years. In developing an axiomatic proof-based approach to geometry, Euclid gave a blueprint for all other branches of math. Non-Euclidean geometry. While Euclidean geometry gave a framework for understanding a substantial amount of geometry, there were other geometric structures which weren't included. This is where non-Euclidean geometry came in. We discussed what it means to be a slightly different set of axioms, as well as introduced some additional branches of geometry. Analytic geometry. Analytic geometry was a turning point in mathematics. The development of a Cartesian coordinate system gave us a new structure to understand geometric objects. Analytic geometry led to the development of calculus, physics, and led to great advancement in a number of fields. Algebraic and trigonometric functions. With analytic geometry giving us an idea of graphs, we now needed new things to graph. Algebraic functions were those built around our idea of binary operations. Trigonometric functions were those built around the motions of a circle. We would later learn that these 2 types of functions describe most anything that moves, grows, or otherwise changes, which is calculus. And so with a variety of different types of graphs available to play with, we could now better understand their structure. And for that, we needed calculus. We began calculus with the idea of limits. How do we define closeness, and how do we define infinity? We then use this to define the idea of continuity, which leads to a greater calculus idea. Derivatives. The derivative is a tool of calculus which allows us to understand how things move, grow, or otherwise change. It turns out with a little understanding of slope and an understanding of functions, we can apply this to a variety of situations. We can then build the idea of equations which use derivatives to describe the motions of all things. Metric spaces. How do we measure distance? In the real world, we measure distance in a number of different ways. Sometimes we want the most direct path. Sometimes we want a path along a series of streets. Sometimes we just care about how long it takes. Having spent weeks on geometry and graphing, this abstract approach to measuring was a natural next step. Measure theory. Having measured distances, our next task was finding ways to measure other types of spaces, and this led to measure theory. Measure theory is often first explored in a general way in calculus, but also becomes essential in understanding later structures in statistics and probability. Chaos theory. When we think about most of the math up to this point, it was fairly clean. Chaos theory changed this. With chaos theory, we were able to see how simple structures allow us to get the chaotic nature of reality. When we think of what the world looks like, it's just a series of simple repeating motions taken for a very long time. Fractal geometry and the Mandelbrot set. Visualizing chaos can be tricky, but fractal geometry and the Mandelbrot set give us a great opportunity to see how simple equations can give beautiful abstract shapes. The Mandelbrot set is just a quadratic with a few extra steps, but look at just how varied it can be. All of this variation is based on small changes in initial conditions. That's chaos. Symbolic logic. Having finished our unit on geometry and change, we started a new unit on truth and uncertainty. To begin with, truth. Symbolic logic is an attempt to use logical certainty to describe the fundamental natures of mathematics. All proofs and deductive reasoning can be described in these terms, and it gives us a basis for understanding what is meant by truth. Logical fallacies. With logic firmly introduced, we had a little bit of fun discussing logical fallacies. While perhaps not math, it introduced a theme for the last portion of the course. There is math which studies certainty, and there are other topics which focus more on uncertainty, falsehoods, and lying. As good mathematicians, we must know the difference between truth and fiction. Combinatorics. Transitioning from truth to lies, we needed to introduce the idea of counting principles. Combinatorics is the study of counting. We can always count one at a time, but sometimes there are thousands or millions of combinations of things, and we need a new technique to count. Probability. We define mathematics as the study of certainty, while probability becomes something which is adjacent but very closely related. It is the measure of uncertainty. While ultimately built on combinatorics and measure theory, probability allows us to ask how likely it is that something will happen. Game theory. And so game theory is a way to introduce competition. Not competition as in predator or prey models, but as in human beings trying to make real-world decisions. When we think about organizations which are in competition with one another or trying to determine a likely outcome, we can use game theory to understand what could happen. Statistics. Statistics gives us tools for understanding data, including how to describe data and how to infer when something is true. It can be a tool to understand how things are related. It can be a tool to misrepresent data and convince somebody of a falsehood. Statistics are things to always question, as it is easy to manipulate data to tell any kind of story. Data analysis. Data analysis and data-driven decision-making are tools of statistics to take data, apply statistics, and use inferences to enact policy. Frequently, it is a misused tool used to justify a decision which may or may not actually have any merit. With mathematics being the study of truth, people often use numbers to justify their decisions. And while there's an appropriate way to do it, always double check the decisions make sense. Final thoughts. We have now surveyed all of mathematics. It is a set of structures which are used to describe all things. With your newfound understanding of mathematics, how would you define what mathematics is? What abstract structures do you use in your daily life? With that, I'll let you get to work, exploring where you find mathematics in your daily life. Take care, folks.